All right, so we're going to be starting chapter 11 with this video, and chapter 11 is the last chapter we cover in this class. It's also the longest chapter. Throughout chapter 11, we're dealing with sequences in series. We're going to introduce sequences in this section, series in 11.2, and then for the remaining several sections, we're going to do a whole lot primarily with the idea of series. But let's start with a definition of what a sequence is. So when we talk about a sequence in this class, we're talking about a list of numbers, typically with these curly brackets in the notation. Kind of generally we'll use A's or B's with subscripts, so A1, A2, A3. And then this dot, 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 or ellipsis here indicates that this list goes on forever. So a sequence is different from just a set of numbers in a couple of ways. One, sets can be either infinite or finite, whereas sequences are always infinite. There's an infinite list here. It doesn't stop at any point. And also, sets of numbers or sets of objects, the order that you write the set in doesn't mean anything. You can rearrange things and it gives it still the same set. But in a sequence, the order of these numbers is important. If I swap some of these values around, then I'm looking at a different sequence. Formally, we can define sequences as functions. We can think of them as functions whose domain is the set of real numbers, 1, 2, 3, 4, and so on, all of your counting numbers. In that case, we can think of f of 1 as whatever the first term of your sequence is. F of 2 is your second term, and so on. Even though that's the formal way of looking at a sequence, we generally don't ever think of them that way in this class. It's just easier to think of them as a list of numbers that goes on forever. Okay, so this notation is common and we'll use it, but it's a little bit more common and a little bit more convenient to use this notation here. So when I have this curly bracket with just a sub n in it, that's shorthand for this entire sequence here. Sometimes we add a little bit more information. We say this notation with this a sub n in the curly brackets, and then on the outside, this thing here that indicates that we go from n equals 1 to infinity. That n equals 1 there, you can have different values. For example, you can have n equals 5 to infinity, which means you're starting at the 5th term and counting on infinitely, but typically we're going to start where n is equal to 1. So our first example, we want to write the first 4 terms of this sequence right here. Now this is a lot of the times what we're looking at with a sequence. You have this curly bracket notation, and the thing that's showing up inside here is the a sub n, but we're giving a specific formula for finding that nth term. So when you don't see these values on the right-hand side here, we assume that n is starting at 1. So if I want the first term in my sequence, I'm going to plug a 1 into this formula. Now there's kind of two important pieces to this formula. There's this -1 to the n power. So when I plug a 1 into that, -1 to the first power is -1. And then when I plug a 1 in here, I get 1 over 1 plus 1, or 1 over 2. So putting all that together, I get -1/2 as my first term of that sequence. Second term, we're plugging a 2 in for n, so I get -1 squared, which is +1, and then 2 over 3. Notice the denominator is always 1 more than the numerator there, so 2/3 would be my second term. Okay, plugging a 3 in for n, I get -1 to the 3rd power, which is -1, and then I have 3 over 4, so that's -3/4. And then finally plugging 4 in for n, because we're counting our way up as we go. That's going to give me a -1 to the 4th power, which is +1, and then 4/5. 1 times 4/5 is just 4/5. And then those are the first 4 terms, but I'm going to do this dot, 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 just to show again that sequence goes on forever. I'm going to adjust my camera here a little bit. Okay. So one kind of good thing to notice here, this is something that we're going to use over and over again throughout chapter 11, is this negative 1 to the n power. What it ended up doing to our terms is it gave us this alternating pattern of negative and positive. So we have negative, positive, negative, positive. We use that a lot. We also use negative 1 to the power of n plus 1 if we want to start with a positive number. We'll see some of that later on. Okay, let's take a look at another example. This time we're given the first 4 terms of a sequence and then the dot, 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 indicating that it is in fact a sequence. And what we're looking for is a formula for the nth term of this sequence. So we want a formula like the one we were given in the previous example, but for this sequence. So here's what I'm going to do. Notice that a1 is the first term of our sequence. It's the square root of 5. And even though we don't normally do this, it's going to be helpful here to put that 2 right there. We already know that if you leave the 2 off, it's a square root, but we're looking for a pattern here. A2 is the cube root of 6. A3 is the fourth root of 7. And there's a pattern here. A4 is the fifth root of 8. So I'm seeing that the type of radical that I'm using is counting up. We call that the index for that radical. It's counting up each step of the way, as is my radicand, 5, 6, 7, 8. So what I want to do is find a relationship between n, which we're thinking of as the subscript in each one of these a's here, and how it relates to the numbers that are showing up in these terms. So for an, what relationship do I see? Well, I see here in this first one, this first term, the index is 1 more than the subscript, which suggests that the type of root I'm taking is n plus 1. I'm taking an n plus 1th root of something. And then when I look at the radicand, the 5 here, that's exactly 4 more than this 1 here that I'm getting in my subscript, n plus 4. Does that same pattern work for these other terms? Well, if n is 2, then 2 plus 1 is 3. That gives me the correct index. 2 plus 4 is 6. It gives me the correct radicand. And you can verify for the other ones. This is working correctly. So this is one way of writing a general formula for the nth term in this sequence. And I have this written up here. I actually don't think I said it. The individual numbers in a sequence, we call those terms. I've been using that now, that word, so just wanted to define that really quickly. A lot of the time when we're dealing with sequences, we're looking at a formula like this that we're either given or we come up with on our own. Sometimes sequences are defined differently out of necessity. So one other type of sequence that you may encounter is something that's called a recursive sequence, or a sequence that's defined recursively. So the way that a recursive formula works for a series is or for a sequence is that you're given the first few, maybe even just the first term of the sequence. It's kind of like a given. And then you're given a formula that doesn't give you the general nth term of the sequence, but rather it tells you how to find each new term of the sequence by using the term before it or some of the terms before it. So a really classic example of a recursive sequence is the Fibonacci sequence. You may have heard of this one before. The way the Fibonacci sequence works is the first 2 terms are defined to be 1. Both of them are defined to be 1. A1 is 1, A2 is 1. And then for every n greater than 2, so meaning once we get past that second term, we define each new term, an, to be equal to an minus 1 plus an minus 2. n minus 1 comes before n. So an minus 1 is the term that comes right before n, and an minus 2 is the term that's 2 terms before a sub n. So basically what this does is it takes the previous 2 terms in the sequence and adds them up, and that's the next term in the sequence. But notice this doesn't give us a formula where we can plug n into something like we did over here to immediately get, like, you know, say the 100th term of the sequence. If I wanted to find the 100th term of this sequence, I still have to count my way out to it. I can't just plug 100 into something. So Here's the first few terms of the Fibonacci sequence. Again, the first two terms are 1, and then to get the third term, I add the previous 2. 1 plus 1 is 2. To get the next term, I add the previous 2. 2 plus 1 is 3. And then 2 plus 3 is 5, 3 plus 5 is 8, and so on. That's how you get the other terms in that sequence. Okay, moving on. So that's some basics on sequences. Now, what we're specifically interested in this class is limits of a sequence, which we'll give a definition for in a minute. But lots of sequences will have this property where as you count further and further out in the sequence, the terms appear to be approaching some specific finite value. That doesn't always happen. There's plenty of cases that we'll look at where that doesn't happen. But we're right now interested in the cases where it does. So think about this sequence for a moment, n minus 1 over n. So the first term in this sequence, you plug 1 in for n. 1 minus 1 is 0 over 1 is 0. And then the next term would be 1 over 2, or 1/2. And then the next term is 2/3, and then 3/4, and 4/5, and so on and so forth. This is what this sequence looks like when I list the first several terms out. This sequence appears to be approaching something. The numbers are getting closer and closer to 1, it seems. And there's a few different ways of looking at that, but right now we just sort of have a gut feeling. If you think about it, these terms are all proper fractions, which mean they're all less than 1, but they're getting bigger and bigger, right? So they're getting larger and larger, but they're still staying less than 1. They just are getting closer to 1 as we get further along in this sequence. So if you were to think about this graphically, remember we said we can think of sequences as functions. Here's the inputs, 1, 2, 3, 4, 5, 6, 7. These red dots correspond to the values of the terms of this sequence. So 0 is my first term, and then 1/2, and then 2/3, and 3/4, and 4/5, and so on and so forth. And if you notice, if I put a blue line here through 1, these terms are getting closer and closer to 1 the further out I go. So that's implying that this sequence has a limit of 1. One way that we can show that is we can rewrite this formula that gives us the nth term of this sequence, n minus 1 over n. This would simplify to 1 minus 1 over n. As n gets larger and larger, 1 over n is approaching 0. So if I think of this as taking a limit as n goes to infinity, because these sequences have infinitely many terms, then this would go to 1 minus 0, or just 1. And that's kind of how we want to think about that. So in this case, that is true. We have a limit of 1 for this sequence. Let's we're going to define a limit of a sequence in two different ways. There's an intuitive definition and there's a precise definition. So starting with the intuitive definition, which is kind of what we just used, we say that a sequence a sub n has the limit L, and we write this. Same limit notation that we're used to with functions. Limit as n goes to infinity of a of n equals L. Or we use this notation as well, a sub n tends to L as n tends to infinity. If we can make the terms of our sequence as close to L as we like by taking n to be sufficiently large. Now these terms are really important. We're going to use these a lot throughout chapter 11. If a sequence has a limit, so if that limit exists, then we say that the sequence converges, or we say that it's convergent. Otherwise, we say that the sequence diverges or is divergent. So down here are a couple more examples of, graphically what it might look like for a sequence to converge. In this case that we looked at up here, our sequence was increasing this whole time, but approaching that value of 1. The sequences can converge in different ways also. So it doesn't have to never pass that blue line. It just has to eventually approach it as close as we want to make it. Here's an example of a sequence where when we graph the terms, it kind of oscillates about the limit L, but ultimately kind of gets closer and closer each step of the way. So this appears to also be approaching that limit of L. Okay, let's talk about the precise definition for the limit of a sequence. This is going to remind you of something you did in Calculus 1 when you gave the precise definition for the limit of a function. It uses that epsilon delta notation, although actually in this case there's no delta, there's just an epsilon. So we say that a sequence a sub n has the limit L, and we write this, again, same notation as before, if for every epsilon greater than 0, there's a corresponding integer capital N, such that if little n is bigger than n, big N, then the absolute value of a sub n minus L is less than epsilon. People have a hard time wrapping their heads around this epsilon delta stuff, or in this case, just epsilon definition. But to kind of help you make sense of it, anytime you see the absolute value of a difference of two numbers, what this is telling you is how far apart those two numbers are. So if I did a sub n minus L and then took the absolute value of that, it's telling me exactly how far apart these two values are on a number line. So when I say that it's less than epsilon, what I'm doing is I'm restricting how far away a sub n is from L. If it says for every epsilon greater than 0, but we tend to think of epsilon as a very small number, as small as we want to make it while still keeping it positive. What this is saying is that if I want a sub n minus L, if I want the terms of my sequence to all be within a tiny little range of L, once I go far enough out in that sequence, there will always exist some number n so that when I go beyond that number in my sequence, this happens. That's basically what this is saying. Now, we're not going to use this precise definition for anything, but in a more advanced class, you would. So we just give it here so that you kind of see mathematically how we think about sequences at kind of a higher level. So here, this image is also kind of showing what we're talking about. If I'm keeping a sub n minus L in absolute value less than epsilon, again, what we're saying is the terms of our sequence, once we get far enough out in our sequence, should be no more than epsilon units away from L. And so it could be it can be no bigger than L plus epsilon and no smaller than L minus epsilon. So again, what we're seeing is our sequence in this example is kind of fluctuating, it's doing its thing, it's kind of, hitting a lot of different values, but eventually it's all the terms eventually are trapped between these two green lines, this interval that's created by this inequality right here. So that's just kind of a visual of what that is. Let's talk about divergent sequences for a second. We can say that a sequence diverges if it does not approach a finite number as n goes to infinity, and we gave that definition on the previous page. But there's different ways that sequences can diverge. So one example is this sequence right here, 0, 1, 0, 1, 0, 1, 0, 1. The terms in this sequence are just alternating between two values. So it doesn't have a limit, because if it did, what would the limit be? It's got to be either 0 or 1, right? But as far out as we go in the sequence, we're still getting infinitely many zeros and ones. They never narrow down to just one limit. So this is a divergent sequence. Another divergent sequence is this one, the one that literally just counts from 1, 2, 3, 4, and onward. There's a clear pattern here, but this sequence diverges because it doesn't approach any finite number. It's just shooting off to infinity. So this one diverges in a specific way. It's an infinite limit. So here's a precise definition for what an infinite limit is. We say that the limit as n goes to infinity of a sub n equals infinity if for every positive number m, capital M, there exists an integer capital N such that if little n is bigger than big N, then a sub n is greater than m. So again, you have to stare at this one for a little bit to understand what it's saying. But basically what it's saying is that I can pick any positive number I want, as big as I want to make it, and no matter how big it is, if this sequence diverges to infinity, then I can always go far enough out in my sequence so that all the remaining terms are larger than that big positive number that I thought of, which means this thing just keeps getting bigger without bound. It's shooting off to infinity. Okay. Again, we don't really use a precise definition, but it's just there for reference for us. All right. So we could also give a similar definition for a limit that diverges to negative infinity. So the next thing we're going to talk about, and I think I'll do this in the next video, but we're going to talk a little bit about convergent sequences and some properties that they have that are useful for the kind of stuff that we're doing in this section. Let's do that in part 2.